Good evening. Thank you all for coming. My name is Doug Hawkins. I'm a VM engineer at a company called Azul Systems. Maybe you've heard of us, maybe you haven't, but we also make a JVM. And I'm going to tell you how a JVM works tonight, at least part of it, how the mechanics of the VM work, when does it JIT, and when does it deoptimize. And if you'd like to follow along, the slides are available on GitHub, as with all the code samples, so feel free to follow the link. I'm easy to find. My username is always DougQH, so. And in addition to being at Azul Systems, I'm also a no fluff, just stuff Java tour speaker, and we have a show coming up in San Diego in April. So. All right. So just a little bit about Azul Systems before I get started. We make 2 VMs. We make Zulu, which is an open JDK offering. It's actually multi-platform, Linux, OS X, and Windows. And we have images available for Docker, Azure, among others. And we do development support, embedded support as well. Our higher end product is called Zing. It's a different JVM. It has a completely different garbage collector designed at being highly scalable. What do I mean by highly scalable? Very short pauses with terabytes of heap. That's not my work. That's actually one of my colleagues in the back there. But that's what our claim to fame has been. My work is actually on what is called ReadyNow, which is support for low latency applications. I'm talking people who measure performance in microseconds. So that's what I'm working on. So first, I wanted to explain what HotSpot's lifecycle is. How does a piece of code actually run in the JVM? We go through a number of phases. We're going to start off in an interpreter, running your Java bytecode. While we're interpreting, we're going to do some profiling. We're going to figure out which pieces of code are used a lot, and also other things about the code. Is this if always true? Is it always false? What type are you using at this particular call site? Those sorts of things. That information is fed into a just-in-time compiler, which spits out machine code. And the interesting thing about a VM is because it's a managed environment, we can do some optimizations that a C or C++ compiler can't do. We can actually speculate that an optimization is correct. It may not be correct, but we have a way to fix the mistake later if it's wrong. In the short term, it'll be beneficial. And if we're right more than we're wrong, it's going to work out to your advantage. But if it is wrong, we're going to have to deoptimize. We're going to throw the compilation away, and we're going to start the process over again. And I'm crazy enough to actually demo all of this to you. But of course, we first have to ask, why would you actually care about this? Well, if you're trying to measure performance in Java, you're going to have to worry about this. Each of those execution phases will run at different speeds. So if you don't know that you're spending your time in the interpreter and that's what you're measuring, you might be measuring the wrong thing. The hot piece of code running in the compiler is probably what you should be measuring instead. There are now good benchmarking libraries that'll help you with that, and you don't have to know the details, but it's good to be aware of it. Now, it will also come up if you've ever done any sort of warm-up. You bring a new node up. Do you want it to run slow right when you bring it up? For a lot of you, that's probably fine. But it's not fine for everybody. Does anyone here actually run a warm-up process, like run fake traffic through their VM? OK, a few. That's about standard. So it does matter. At least not for everyone, but definitely for some. Let's jump right in. A very simple program. I've got a main. I've got an outer loop that I'm going to iterate over 250 times. The outer loop is measuring the performance of this inner loop, which is just allocating objects, 1,000 at a time. So we're just measuring how long does it take to allocate 1,000 objects. So I'm going to run that program. This is the program. It's running. It spits out a bunch of numbers. We can see the numbers start quite high, and then they drift all the way down to 0. Yes, 0. So let's plot that. Have a better picture of what we're seeing. OK. So here's what it looks like if we plot it. This is our chunks, 0 to 250 at the bottom. And that's our nano time. OK, we have 3 gigantic spikes. You're probably not going to be surprised. Those are GC pauses. Those are where we did garbage collection. But we're missing some very interesting detail if we look at it like this. If we switch to a log scale, we see a more interesting pattern develop, which is we see this one plateau, and then it goes down some, and there's another plateau, and then it drops all the way down to 0. We still have the 3 GC spikes, but we have these 3 different phases of execution. That's actually the interpreter, the first phase of the JIT, and the second phase of the JIT. That's what's going on here. Even a simple program like this, you'll see radically different measurements from beginning to end. Let's make it a little more complicated. This time, on the 200th iteration, I change a variable that I had set to null at the very top to actually being equal to some object. And in the inner loop, I check that. And if it's not null, I print out trap, and then I set it back to null. How could that possibly matter? Well, that's one of those speculative optimizations I was talking about. It's not expecting that trap variable to be non-null anymore, or to be non-null. And when it sees that, it deoptimizes, and performance goes back to the same level we started at. And then we can follow the same progression down again. So it doesn't take much to actually start to hit these interesting behaviors. All right. So now I'm going to start to break it down a little bit at a time. That's a high-level example just to frame what we're talking about. The interpreter. This is, of course, where we start. It's, as interpreters go, pretty clever. It's actually dynamically generated when the VM starts up. It's a threaded interpreter, which is a way of reducing the branching so that it'll run faster. But as compared to the JITs, it's still really slow. It's about 10,000 times slower than the JIT. So you really don't want to spend much time here. And fortunately, you don't. The more interesting part of the interpreter's job is to identify where the hotspots are. That's where hotspot gets its name. We just want to know what code are we running again and again and again. Those are the things that are worth compiling. If we compile those, we'll get almost all the benefit. Step 1 to identifying what to compile is something called the invocation counter. And it's what it sounds like. We track how many times a method has been invoked. Hotspot is a method JIT. It compiles whole methods at a time, more or less. There are also trace-based JITs. Dalvik, for instance, was a trace-based JIT. But Hotspot is method-based. So one way to track what's hot is to just track how many times a method is called. So another simple example, a loop from I equals 0 to 20,000, call a hot method. Hot method is decidedly uninteresting. I don't know of a way that is available in a product build easily. No. So you could do that, but the instrumentation will itself perturb the behavior of the application. So that probably won't work out exactly how you'd like. So I know that 20,000 calls is going to be enough to get this method compiled. When it gets compiled, what actually happens is the Java thread enqueues a compilation job for a background thread, a compiler thread. But it just enqueues it. It's not available immediately. So if I just let this program terminate at the end of my loop, I might not see the compilation get done. So instead, I'm going to sleep for 5 seconds and make sure the compiler has enough time to actually get to it. So I'm running these examples with print compilation. I'm also running them with minus tiered compilation. I'm doing that just for consistency between Java 7 and Java 8. As we'll see a little later, tiered is off by default in Java 7 and on by default in Java 8. This way, you can run the examples with either one. You're going to get the same behavior. I will show you what it looks like in tiered later. But you turn on print compilation and you see output like this. It's showing me what's getting compiled, and indeed, my hot method got compiled. And it's showing me the size in bytes. Why is it 1 byte? It was empty. What's a 1 byte? It's the return statement. You don't have to write an explicit return, but there is one in the bytecode. So how do we actually read this output? There's quite a bit of information in that output. So we look at this, and the leftmost column is a timestamp when the compilation was completed in milliseconds since the VM started. The next column over is the compilation ID. The IDs are assigned in the order in which they are enqueued, so they may come out in a different order. Then we have a method name. No arguments included, which is important later. And the method size in bytes. And if it's a native method, it just says native. And then we have all these little funny single characters. The N is for native, so that's redundant. The bang is for exception handlers. If there is a try-catch inside of the method, you will see a bang. Also, actually, if you have a synchronized block inside of the method, you will see a bang, because that's done as a lock and then an unlock inside of a finally block. That's what it compiles to. So it's still an exception handler. S is a synchronized method, so synchronized on the modifiers, not a block within the method. And then there's a %sign. This is what HotSpot calls an on-stack replacement. It's sort of a misuse of the term, but it is the compilation of a loop inside of a method. And when you have one of those, you will also have an index, which is the bytecode index of the loop. This can be a little hard to read because argument types are not included. So I can have something like this: Java NIO buffer position 5 bytes and Java NIO buffer position of 43 bytes. Those are two different methods with different overloaded arguments. Here you can probably guess that the one is 5 bytes is a wrapper around the one that is 43 bytes, which contains the real implementation. All right. There is another counter as well. If you noticed, if you were watching very carefully, you probably saw that main got compiled at the end of my previous example. Well, main's only invoked once. How does that make any sense? That was caused by this counter, the back edge counter, which is a fancy speak for you're going backwards in the code. It's a loop. So we count how many times we go around a loop, so we have a way to trigger those loop compilations I was just telling you about. So again, a loop from 0 to 20,000, call a hot method, wait for the compiler. Another loop from 0 to 20,000, call a hot method, wait for the compiler. You'll get this output. Main got compiled. It's only been invoked once, but it got compiled. And it's one of those OSR loop compilation things. You can see by the %sign. And this is the loop at bytecode index 5. And then we had another one for the loop at bytecode index 37. Why do we need this? Well, there are methods that really only get compiled once, that only get invoked once. Any sort of event loop, whether it's handling request response from a server, swing events, what have you, you're probably only running it once, or at least once per thread. It's not going to get called 10,000 times unless you have 10,000 threads. So it's important because it's the top level thing, and yet if we just use the invocation counter, it wouldn't get compiled. So we have this back edge counter instead. We count how many times we go around a loop, and if that number is high enough, we do one of these loop compilations. The reason this is called on-stack replacement is because you have to think about, I have a stack. Right now, all of my frames are interpreter frames. And I get to whatever my event loop method is. I would like to switch mid-run of this method from interpreted to compiled. So I have to copy all the data from the interpreter frame somewhere, put the compile frame on top, and put all the data in place, and then start things running again while the frame is actually on the stack. So we swap out one representation for another while it's on the stack. And we can actually do this in reverse as well. It's actually a general technique. We can use this for other purposes, and we will. It's the basis for deoptimization as well, going the other direction. But HotSpot uses the term to mean these loop compilations. If you've ever read anything about how the JIT triggers, that's probably as much as you've seen. And that's almost the complete picture, but not quite. The two counters actually work together. It's not just one or the other. It's not we reach some threshold for one counter. It's actually we reach some threshold for the sum of the two counters together. That's what triggers whole method compilations. It doesn't trigger the loop compilations. So in this case, I've got a loop, which is longer than if I had just written this out, but I call outer method twice. That's it, twice. And then outer method calls inner method 10,000 times. OK, so clearly inner method should get compiled because it's going to be called 20,000 times. And we've seen that that's enough. And maybe outer method will get one of those loop compilation things. Yes, that's a possibility. But outer method will also itself be compiled. The whole thing, not just the loop. If you run that example, you'll see, yes, inner method got compiled. We expected that. Outer method did get a loop compilation, but it also got a full compilation. The reason is we have two invocations, but our back edge counts are actually cumulative across each invocation. So that means we have 20,000 back edges, 2 times 10,000. The sum of those is 20,002, which is apparently enough to actually trigger compile. So they do actually work together. This works out well if you have a method that's, in its invocation count, is only sort of lukewarm, but it has a relatively long loop inside. We'd still like to compile that because there's still a piece of code inside of it that we're running 10,000 times or 20,000 times. It's worth compiling. So the two counters work together. So far, I haven't actually told you what the threshold is. I mean, I pulled this magical number 20,000 out of nowhere. I know that that's enough, but why didn't I just tell you what the number is? The reason is there's not one number, or at least historically there wasn't one number. Historically, we had two versions of HotSpot, a client version and a server version, with two different numbers, and actually with two different JITs, two completely different compilers. And these two VMs were targeted at different use cases. The client VM was designed for Swing applications and applets. How many of you are writing Swing applications and applets? Oh, you're a plant. Right. It hasn't really worked out the way Sun intended. But the idea is, as an end user, I want my applications to launch quickly. How many of you like staring at Eclipse's splash screen? It's pretty, isn't it? No, none of us like staring at Eclipse's splash screen. So we want our application to start quickly, which means getting it into machine code quickly. But after that, I'm a slow human. I'll barely notice a 50 millisecond hiccup. That really is a UX guideline, is to give someone a visual response in 100 milliseconds. So like 50 milliseconds, I could just be completely oblivious. It doesn't matter. I'm slowly dragging my mouse across the screen. The computer's just waiting there. What the hell are you doing? Right? It doesn't need to run all that fast, except in a few key places. So it doesn't need to produce the best code. It just needs to produce it quickly. That's what the client VM is for. It is a fast-acting compiler. It compiles very quickly, just not the greatest machine code in the world. So it runs relatively slowly. Relatively is still, 5,000 times faster than the interpreter, probably. But it's not as fast as its server kin C2, which is the compiler in the server VM. It is a smart compiler. It works hard to produce good code. But it's relatively slow. It's designed for server applications, of course. Your ops person doesn't really care that it takes an extra minute or two to start WebLogic in all likelihood, except when a server goes down. You as a developer probably find it really darn annoying. But you're atypical. It doesn't really matter that our servers take an extra minute to start. So it's not trying to start quickly. But after that, it could be thousands of humans on the other end, or worse, thousands of computers on the other end. Then we actually care about raw speed. That's what the server compiler is for. So it produces compilations relatively slowly, but the code runs usually about twice as fast or more than C1. C1 kicks off when the threshold is a mere 1,000 invocations plus back edges. Whereas C2 wants to take its time and gather as much information as it can, it waits for 10,000 of these. And part of the reason for that is C2 is an interesting animal in that it is a profile-guided compiler. It really wants to have data about what your program is doing so that it can optimize for exactly that. That extra window allows that to occur. When you're using C2, the interpreter does extra work, not just tracking invocations and back edges, but also tracking things like, was this if always true? Or was this always false? Or 99% of the time it was true? Or you're calling object hash code here, but almost every single time you call it, it's actually a string. So I'm going to optimize for that. Those sorts of things. And it can speculate based on that information. That information may eventually be wrong. Your application might start suddenly hashing something other than strings. But the VM has ways to correct for that, as we'll see later. All right. So now you're wondering, why did you bother to tell me about this C1 thing? We already agreed nobody is writing Swing applications. There's not actually a client VM anymore. Right. But in Java 8, and also available in Java 7, but not on by default, is what's called tiered compilation. The goal is to get the best of both worlds between C1 and C2. We're going to use C1 for quick startup, but then we're going to have a way that if something's used a lot, to move from C1 to C2. The thresholds change a little bit. We move from the interpreter to C1 not at 1,000, but at 2,000, and we move from C1 to C2 not at 10,000, but at 15,000. But the idea is basically the same. And now C1 also does extra data gathering for C2 as well. This was a long talked about and finally delivered change in Java 8. Unfortunately, it produces somewhat unstable top-line performance, so most people who are worried about performance benchmarking turn it off.
So before being off in Java 8, does it imply that in Java 7 this feature is not as stable?
I don't know how much they've tweaked it between then, so I'm not sure. Certainly they continue to change it. I'm only going to explain the basics of how tiered works, but it has this rather complicated adaptive policy. I've included a link here at the bottom to a more detailed presentation by the Oracle developer who actually worked on it. So you could go download the slides and follow that. So. Tiered compilation isn't quite as easy as what I just described. There are actually 5 tiers in HotSpot. Tier 0 is the interpreter. This is where we start. Same as before. Tier 4 is C2. This is our end goal, usually, just like with the Server VM of old. Tiers 1 through 3 are all C1. Why? Well, they're C1 with different extras. So first, there's plain vanilla C1. Doesn't have anything extra, just produces the Java code that you wanted. Then there's one that has counters. It has those invocation and back edge counters I was talking about. We need to have them if we're going to have a way to know when we've reached a threshold where we're going to trigger a C2. So we have to add that. And then C2 would like to have that detailed information about what this individual instruction was doing. So tier 3 adds that on top of the basic counters. So which way do we go in an if, that sort of stuff. The common flow is actually to do exactly what I showed you in the previous slide. Go from 0, not to tier 1, not to tier 2, but all the way to tier 3. Where we have counters and the detailed information C2 wants. When those counters go past their threshold, we go to C2, and C2's got everything it needs. That's the normal flow. But C2's slow. C2 might get backed up. As the application is starting, there's a whole bunch of compilation going on at the very beginning. Everything started at the interpreter. We're figuring out what's hot. We're scheduling compilations like mad. The compilers are overworked. So in that case, C2 may not be able to get to our method anytime soon. If that's the case, we don't go from 0 to 3. We go from 0 to 2. 2 just has counters. Then when we go over the counter limit again, we say, C2 looking less busy. Will it actually be able to get to us sometime soon? OK, we'll go to tier 3 and get the information C2 needs. Why don't we do that right away? That detailed information comes at a cost. It's about 30% overhead. So we're trying to avoid that overhead until we're actually going to be able to use the information we're going to get from that. But if C2 is freed up, we'll move to 3, and then we'll have the data after the next tripping of the counters to go to C2. And the last case, it's kind of a weird one. It's a trivial method. In this case, we start in 0. We go to tier 3. And C1, during the course of doing the compilation, says, you know what? This method's pretty easy. There's nothing really interesting here. Nothing that C2 is better at than C1 is. So rather than spending the time on C2, which is in some sense a scarce resource, C1 just does it itself. And it actually goes backwards to tier 1. That seems odd. Yes, but this is C1 with no overhead. We don't want the overhead of counters and detailed profiling if we don't need it. The idea here is, for a trivial method, tier 1 C1 with no overhead is just as good as going to tier 4 C2. And that actually happens immediately. We don't even wait for counters to trip. This I will actually show you the demo for. OK, we've got a loop. We've got a method. We're going from 0 to 3,000. That will be enough to trigger our C1. We're going to wait for 5 seconds to make sure the C1's ready. Do another 20,000. That'll be enough to trigger a C2. And then we're going to wait another 5 seconds to make sure the C2 is ready. But I want you to see all those different behaviors I was talking about, so I wanted my method to actually do something this time so that we get some other stuff compiled. So I decided to print out the null character. Yes, that's right. I'm printing out absolutely nothing. But that's enough to cause a whole bunch of I/O methods to get compiled. So we'll see a whole bunch of I/O stuff get compiled. Let's actually run this one. All right, that's the program. Let's run it. OK, a lot more things got compiled. Let's pick out a few interesting ones. There we go. First up, object init. Now we've got an extra column in our output. We have this third column here. This is the tier at which we're compiling. You can see almost everything is starting off in tier 3, just as I told you it would. And object init is a classic case of a trivial method. It is nothing but a return statement. It's a single byte. So we can see we had a tier 3 compilation at 57 milliseconds into the run. And immediately, and I mean immediately this time, 58 milliseconds into the run, we completed a tier 1 version of it. It did not wait for the counters to trip again. And then we see this line. Same compile ID from above, compile 5, object init, but with this text out to the side, made not entrant. What that is saying is, I am throwing this away. Well, OK, not throwing it away. I'm not letting anybody else use it yet anymore. Once nobody's using it anymore, I can throw it away. I'm going to start giving them to the tier 1 version instead, now that it's ready. All right, so that's a trivial case. And let's go find the normal path. Yeah, here we go. I can't find the first one. Anyway, stream encoder write bytes is now getting compiled at tier 4. And we're retiring stream encoder write bytes that was previously compiled at tier 3. Now this happens after the second 5-second pause. So during the second heating up phase. It didn't happen immediately. But that's how tiered works. And it works OK. I think it still has rough edges. Going back to our example from the very beginning, we now understand what is happening here. This first plateau is us running in the interpreter. Remember, this is log scale. This second plateau is us running in C1. I actually did verify this by looking at the print compilation output. I'm not just BSing you, I promise. And this third one is running in C2. And you're probably still not believing those C2 numbers, but we'll get there. All right, so we talked about how we actually trigger compilations. Now we're going to talk about what kind of optimizations the compilers can actually perform. First off, every compiler has something called intrinsics. It's just special code that the compiler knows about. It knows what malloc does, or new does in Java, or array copy, those sorts of things. Things that happen a lot, or maybe have special semantics that are built into the VM. And they're not written in Java, usually. Or they're written in Java and then we just ignore that. I'm going to actually show you that. They're written in machine code or they're built into the compilers directly. All of those things are true in HotSpot. And they may use special hardware capabilities, so array copy will actually use whatever vectorization capabilities your hardware has, whether it's MMX2 or AVX2 or whatever. We're going to use an array copy that takes advantage of that. So some examples. Usually they're small things. Array copy isn't really that small, but math min, max, sine, cosine, tangent, which Intel has special support for, those sorts of things. And high errors for, but that's another issue. Those things are just built in. After that, we can start to do some basic simplification. And you actually take a compilers class? Did you actually do any optimization, or was it all parsing? Yeah, that's, I find that unfortunate, but okay. I had to implement one optimization in my compilers class, and this is it. Common subexpression elimination. So here I have A equals B times C plus G, and D equals B times C times E. Okay, so I have a common subexpression B times C. I could extract that out into a temporary variable, and that would probably make things a little bit faster. Yes, we can do that. We can do other interesting things. We could do loop unswitching, as it's called. So I have this if is debugging enabled inside of my loop. But in this case, I've assigned it to a local variable, so clearly it's not going to change value during the loop. So we could actually rewrite this to have one copy of the loop where we know it's true, and one copy of the loop where we know it's false, and one of them has a call to debug and one of them doesn't. It might actually be able to do this even if I didn't pull the call out into a local variable, but that requires more work and more explanation, so I'm keeping things simple. We can also do dead code elimination. Imagine for a moment that somehow the compiler knows that ArrayList index of is not receiving a null. That's probably not the common case. Well, then this whole first part of ArrayList index of is just not used. It's dead code. We don't need it. It never happens. Just get rid of it. Okay, but how could it possibly know that? Well, we need some form of interprocedural optimization. We need knowledge that spans across the call boundary. If we know that our callers, all of them, potentially, never send us a null, we could do this. Or if we specialize the code for this particular call site, maybe by doing something called inlining, where we just embed the code inside of it, then now we know that that value is not going to be null. Usually people just think of interprocedural optimization, they think of inlining, and for HotSpot that's fine because that's about all HotSpot does, but that's a little bit simplistic. But inlining really is probably the single most important optimization you can do because it's a mother of all optimizations. It lets us see beyond these boundaries and let us do other interesting optimizations, like getting rid of that dead code in ArrayList index of. What can we inline? Well, small things are good candidates for inlining. Intrinsics tend to be small, so yes, they get inlined. We'll take this example. I create a bunch of random integers, 100,000 of them. I find the minimum one by using a loop, and of course the usual sleeping for 5 seconds. We're going to run this. And this time I'm actually using some extra options. Beyond just the print compilation, you can see I'm now actually running with this cool sounding thing, unlock diagnostic VM options. That lets you get at things that we don't really want you to use, but we'll let you use them. There are a whole bunch of things I could show you if I were willing to use a development VM, but I wanted to stick to things that you can actually do yourself. That option doesn't actually do anything. It just lets you use other options. And in this case, I'm using print inlining. And we can see a whole bunch of things got inlined. We get this inlining tree. So each of these lines is a call that got inlined. That's telling me the bytecode index of the call. So current thread got inlined. It's an intrinsic. Same for this thing called unsafe get long. It got inlined. And then we can keep going down. Here's another level of inlining for thread local random next seed and the things inside of it. But of course, the real point is math_min is an intrinsic, and it did get inlined. What the heck is this line? Why does it say math_min contains 11 bytes of Java code? Because math_min contains 11 bytes of Java code. There you go. There's the Java code. Yeah, we don't use that. Well, we might use it some of the time. The rest of the time, we're just going to use what's built into the VM. That's what an intrinsic is. We're free to replace it with something we know is semantically equivalent. We only do these things for things that are in the JDK that we expect you won't touch. So if you were trying to be mean and put a math_min on your bootstrap path for your coworkers that changed it to max, I'm afraid that may not work. I haven't actually tried. It'd be even more fun if it worked some of the time and not the rest of the time. But we can do this with direct calls too. What do I mean by direct calls? Well, anything that we wouldn't tag with virtual in that C++ language that none of us use, right? In Java, it's static calls, private calls, and constructor calls. They don't require dynamic dispatch. And dynamic dispatch doesn't mean invoke dynamic. It just means polymorphism. So let's see that. Same basic game as before. This time I'm actually pumping my output to a null print stream. So it's going nowhere. I'm calling a hot method inside a loop, sleeping, as you're probably getting used to by now. And I'm calling a method square, which is decidedly uninteresting. It's just x times x. And I'm calling it with constant values, 7 and 9. We can actually just inline this and say the square called with 7 is 7 times 7. And then we can actually simplify that a step further and just constant fold it down to 49 and 81 respectively. OK. I could show you the print inlining output. It would look like this. There is some interesting stuff here in that you can see that println actually didn't get inlined. That's what this bang im out here is, because it was already compiled into something that was pretty big already. Yeah, HotSpot does that. Order of compilation matters. I question whether this is a good idea, but that's a whole other side topic. But it did inline square, and you can see it inlined it twice. This is the call with 7, this is the call with 9. That's hot method, and then we have this OSR compilation inlining hot method and in turn inlining square twice. That's not really fun. Let's take it up a notch. Let's actually look at the assembly code. Yes, you can do this with a regular VM. You're going to have to tweak it just a little bit. You have to go and download an extra add-on disassembler. Assuming you're using x86 64-bit, it's going to be called hsdis-amd64, and then whatever the suffix is for your platform, DLL, SO, dylib, whatever. You go find it, you download it, drop it into your JRE lib directory, and now we can run with, we could run with print assembly, but that would print the assembly of every single method that gets compiled. That's going to be a little overwhelming. I'm going to do just the assembly for the method I'm interested in. In this case, it's going to be the hot method. So I'm going to run my example with unlock diagnostic VM options, compile command, print, and the method. And note it's slash separated and uses colons. Yeah, a bunch of C++ programmers wrote this, i.e. people who actually work on the VM. All right. So we're going to do that. Is example 7. Oh, I have it turned off. Okay, that's the inlining. Pardon me for a second. I'll actually print out. I'll show you the assembly too. Yeah, if you download all the code samples, you'll see they're annotated with these things that tell you what you need to run with and what sort of highlights to look for in the output. They also happen to be what is used to generate my scripts so that I can run my examples. So there we go. This is the assembly. It's rather long. Here are invoke virtual println calls. They're in a few places. But the interesting part is here. This OX31, that's the hex for, well, 7 times 7, 49, being passed to println. So there is no call to square anywhere, which is good. It would be a lot of overhead to do that just to do a single multiply instruction. But inlining is way more than that. That's another compiler talk entirely. Okay. Another optimization that's been the holy grail of Java for a long time, finally I think got turned on by default in Java 6 and actually became useful in Java 7. Escape analysis. The idea is if we have an object that we're allocating, if we know it never leaves this stack frame, then we don't need to allocate it on the heap. We could allocate it on the stack. A good example for this is an iterator. So you might write a for loop like this, for long x in list, assume list is an array list, and sum up all the elements. Well, that's really just syntactic sugar for this. Iterator long, iter equals list iterator, iter has next, iter next. Which of course allocates a new iterator object. If we inline iterator, we inline has next, we inline next, then we will, and the constructor of the iterator itself, we can get to this. This is slightly simplified from what it would really be, but it's close. Our first part of our for loop was getting our iterator. So that's really constructing one and calling the constructor. So we allocate and call the constructor. The constructor does this. We have 3 member variables, size, cursor, and last ret. We initialize all those. We don't actually need any space for this object whatsoever. We can just have them all as locals. We could do that. Then we can do inline has next, which just becomes iter $cursor equals iter size, or not equal to iter size. Then we can inline next, which becomes this lovely little mess. And there. No allocation whatsoever. This is possible. This does happen. At least it happens very well with iterators. And other things, like objects that someone was creating inside of a for loop and not doing anything with. Which is how we get to our simple program behaving the way it did. That call to new object was really actually an allocation of the size of an object and then a call to the constructor. Well, the constructor's empty. We inline it. We don't have any work to do. OK, that's good. Then we've got this object we just allocated. Nobody's using it. It's a dead store. We don't need that. OK, we now have an empty loop body. Let's just get rid of the loop. We don't need that. All right, so what's left? Well, this loop is gone. There is no inner loop. So what are we measuring? The time from one call to system nanotime to the other call to system nanotime. That's it. Now, system nanotime doesn't actually have nanosecond resolution, at least not on my Mac OS. It has 1,000 nanoseconds of resolution. So I'm either going to get a difference of 0 or a difference of 1,000. Yep, 0, 1,000, 0, 1,000. That's what's happening. This is the dead code elimination with escape analysis, with some inlining all put together. C2 just got rid of it altogether. We just have a timing loop that doesn't time anything. All right. Now, to me, that's all boring. That's all static optimization. Any C or C++ compiler could theoretically do all of that. Let's get to the things that only a VM can do. Speculative optimizations. Let's see how I'm doing that. Okay. Now, one of the nice properties of Java is we don't get seg faults. Instead, we get null pointer exceptions, which I'm sure we all agree are much, much better. Okay, maybe not. But at least our program won't necessarily die. To do that, we have to put null checks everywhere, right? No, 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 no. Let's see. Okay, I've got a hot method. I'm calling it with the string hello. Hash it should have been called hot method. Knew I would miss something between changing my code in slides. So in one loop, I call it just with the string hello, and then I switch to calling it with null. And I catch the null pointer exception, and I claim that I'm tempting fate. What's going to happen? Let's run this. All right, so hot method got compiled, as we would expect. But this time, hot method has specialized for the fact that it's never seen a null. What happens when I show it a null? Well, the first time, nothing much seems to happen. There is something going on here, of course. Second time? Nah. Third time. What's this about? Hot method got thrown away. Why? We reached our limit. We decided, okay, apparently nulls are a thing now. We're going to have to deal with that. And the way we've been dealing with it is non-optimal. How were we dealing with it? Well, let me show you what the assembly was before. It was this. Again, I forgot to update that. Here is our null check. What? There's no comparison against 0 there. Yes, that's correct. There is no comparison against 0 there. And it's got this little comment in the assembler. Yeah, we actually comment assembler. It says, implicit exception dispatches to this address. What does that mean? Well, it's just going to load whatever's at that address. And what happens when you load something, a null, in machine code or C or what have you? You segfault. Yeah, we segfault. That's exactly what the VM does. It segfaults. The problem is that adding that test, it's slow. Branch instructions are like the worst possible thing you could do for hardware, even though we could predict this one perfectly. So we don't do that. The loading of it is a test. It's a test by the memory subsystem. And we just segfault. But it's a managed environment. We can do things that your C or C++ program cannot. Well, or at least you don't do by default. We've installed a signal handler to deal with segfaults. So you cause the segfault, null pointer exception. The signal handler catches that, handles that. And we say, oh, I'm sorry, segfault. I meant null pointer exception. That's what it is. They're really the same thing. Now, as you probably guessed, going through a signal handler all the time is not the fastest thing in the world. If you don't do it very often, with nulls aren't a thing, which please tell me your programs are not producing null pointer exceptions all the time, this is fine. We've saved cost on the check, and that's beneficial. But if nulls are a thing, this is going to hurt. So we stop doing that, and we actually do switch to an explicit check. In HotSpot, as you've seen, the number where we switch is 3. 1 null, we're like, okay, maybe. That's not so bad. 2 nulls, dicey. 3, okay, that's it. No. That's when we switch. There is a flag that controls this. It's only available in development builds. You can't set it. Too bad. So there are different ways we can deal with deoptimization. Oftentimes it'll result in a bail to the interpreter. Where the compilation can't handle it, we're going to go back to the interpreter. In this case, we're popping the stack frame anyway, because we're throwing a null pointer exception. So, well, unless there's a catch, but it probably doesn't matter. Once we've done that, we can decide, are we going to keep the compile? For nulls, it's if we've seen less than 3 of them, we'll keep it. Otherwise, no, we're going to throw the compile away. And then we can decide, do we have enough information and make a new compilation now? You know, okay, 3 nulls is our limit. Okay, we're just going to recompile with an explicit null check. Or do we need more information? And we'll see a case of that a little bit later. This one is the at 3, no, throw the compile away, but go ahead and make a new one right now. All right, another flavor of this, hot method checks a volatile variable thing, which is initially set to null. And if thing is null, it prints out the empty string. If thing is not null, well, it prints out the empty string. These are radically different behaviors. So we're going to warm up with thing being null, wait for it to compile, then we're going to change it to something non-null. And then we're going to call it some more. What's happened under the hood is this block, which is really this single statement, has been replaced with what's called an uncommon trap. This is just a piece of code that we've decided based on profiling is dead. We didn't statically prove it's dead. We just said, based on what we know so far, it's dead. We're going to go with that. And I violated that assumption when I changed my variable. Compiler people call this a phase change in behavior. So your application was doing one thing, it started doing something else. Shame on you, we haven't optimized for that. And that's the sorts of things that lead to deops. All right, so unreached hot method does get compiled. And as you can see, after the 5-second mark, when we switched to using a non-null, it deoptimized, and we replaced it with another one. This time without the assumption. I can run it for as long as I can want. I can switch back and forth. Now that I've exercised both blocks, it's got code for both. It's not going to deoptimize again, at least not there. Okay. Now, when we did this deoptimization, we actually did this bail to interpreter, which is really an on-stack replacement in reverse. We had a compiled version that couldn't handle printing out the empty string instead of printing out the empty string. So we hit that trap, and that actually kicks us back to an interpreter instead, which always can handle everything. But, of course, is 10,000 times slower. It's like, okay, why do you even bother with this speculation stuff? I mean, if you think about that previous case, how did it know it was wrong? Didn't it have to perform the check didn't have to check whether it was null? Yes, it did. So we didn't really gain anything. Yeah, that's true. Not in that particular case. But we'll take a silly toy case. We got x equal to 0, y equals 25. That's actually a dead store. Then we have a condition, and we may go left or we may go right. We'll assume for now we're going left. Y is equal to 15, not y is equal to 20, negative 20. And then after that, we do y times equals 2. All right, well, we could simplify the code now that we know that the right branch doesn't happen. We could just constant fold 15 times equals 2, that's 30. I guess that's something. Not much, but we haven't gotten rid of a branch yet. What's the point? Well, imagine there's another branch past that that's if y is greater than 0. Okay, now we can prove that that's not true, assuming y isn't too big and we're going to overflow, but you know, in this case it works. So now we can start getting rid of branches. Optimizations, they build upon themselves. It's not that one optimization is necessarily going to get you a lot. They just build and build and build on each other. So that's why we're doing these sorts of things. All right? So now we know what happened in the not so simple program. We hit this point. That's when I switched my null. And we went back to the interpreter. We bailed. The real magic of HotSpot is virtual call inlining. This is something C or C++ really can't do. They can do it in some limited cases, but this really requires profiling. We need to know what types are using at a polymorphic call site, and then we can do some interesting things. There are two parts to this. There's what's called class hierarchy analysis. This is based on what classes are loaded right now in the VM, keeping in mind that classes are loaded lazily. And then there's also a type profile. What types are used at this call site? Step one is the class hierarchy. So imagine I have a class function. It's abstract. It has an abstract apply method. It takes a double, returns a double. And I have two implementations, square and square root. But right now, I've only loaded square. Haven't loaded square root, never used it. So if I call func apply, what must I be calling? Square apply, or I'm getting a null pointer exception. Those are our two choices. Right? Either I don't have an object, or it's a square. Those are our choices. Okay. We can inline in this case. So I have a function. I set it equal to a new square. I call and apply helper method, passing it a function and an int, my index, and that's it. I do actually return the value, although I'm not really using it. And of course, there's the sleep for 5 seconds. Once again, we'll run this with print inlining. There you go. Here's our compile of monomorphic apply. That means one type. There's square apply getting compiled. OK, fine. But here's main getting compiled. It's apply method getting compiled inside of it. And it's inlining square apply. It does know that only squares are being used, and it did inline it. Now, to be fair, C or C++ could have gotten this one. You can actually deduce, if you try hard enough, that I set func equal to a new square, and I never changed it. So func is always a square. Therefore, if I go through all of this, I can get to the point where I say, I must still have a square at the end. That's not how HotSpot did it. But C or C++ could have done it that way. OK. Unfortunately, there is a bit of a storm brewing here. What do I do after monomorphic? What's next? How did this actually get compiled? I'm not going to show you the assembly this time. I've got my function. There is actually no check here. Before, with the if equal to null, there was actually a check for the unreached case, not for the implicit null. Here there isn't one. It's working solely based on the fact that there has not yet been another class loaded. And that's it. If that changes, we got to do something about it. This cannot realize it's made a mistake. There is no way to bail from here. So we've inlined our square. Great. What happens when we load another type? Well, square root, for instance. OK. Let's up the ante a bit. We got a square. We're going to call not just one apply function. We're going to call 8 of them. Yes, all in the same loop. You can imagine these calls are scattered all throughout your program. This is easier to write as a demo. We're going to warm them up all with square. We're going to wait for the compiler. And I assert that a deoptimization happens here when I merely hint that there is the notion of a square root class. Note, I didn't actually use it. That's more than's required. All right, so all 8 apply methods got compiled, just as we would expect. And what is this? As soon as I load that class, that assumption is wrong. And they have no way to detect that later. They have to die, and they have to die now, or they will make mistakes. They are all killed immediately at a stop the world pause. It is not just GCs that pause your VMs. There are other things. Admittedly, GCs dominate for most of you by many orders of magnitude. But there are other things that do stop the world. And this is order in, not based on methods, number of methods, but based on the size of the methods, actually. And I am actually running with an extra flag that shows those other pauses, which you can see here, deoptimize. That flag is actually available without the diagnostics stuff. You can run with this. Print save point statistics, and you also have to use this print save point statistics counts equals 1. What that means, I have no idea. It gets the output I wanted. All right, so that is actually stop the world pause. What happens after that? Well, then we switch to an explicit check. So now we switch to func get class equals square.class. Note, this is not an instance of check. That will be important later. And we inline the body there, else a trap for the class check. This is the kind where we can bail later, because we actually have a check inside the compilation. It doesn't have to be at a stop the world pause. We can actually do this one more time. We can get a second type inlined. Once you get to 3 types, I'm sorry, what's wrong with you? We're just going to go back to a plain old dynamic call. That's the megamorphic case. And we just give up. All right, see the whole workflow. I got a square. I'm using 2 apply functions because 8 was a little overkill. I'm going to load square root. I'm going to continue to use just apply 1 with just square. Then apply 1 with also square. And then apply 1 with another square. And then I ran out of room on the slide, but apply 1 with yet another square. Here, when we load square root, we're going to get that stop the world deop now. Then we're going to specialize apply 1 for squares. Then we're going to hit that trap, because we're only dealing with squares. When we introduce a second type, that'll be a deopt. That's just a bail to the interpreter. Then we'll introduce another type, a third type. That will fail because we have if square, if also square, else trap. That'll fail with a different deoptimization, and then we're back to just doing a plain old virtual call. All right, so apply 1 and apply 2 got compiled. We load square root. I did my printing a little differently, so those got made non-entrant at the stop the world pause. Then we specialized apply 1, so it got compiled again just for squares. We introduced another type. The previous one got made non-entrant. We compile again. We introduce another type. Previous one gets made non-entrant. We compile again. And then we introduce another type, and we don't deopt because we're now just back to doing a vcall. We've given up on being optimistic. This actually does work really well. Most call sites use 1, maybe 2 types. I mean, 90+% of call sites use 1 type. Really. I've done the statistics. I've actually traced applications. Another like 5% use 2 types, and then everything else after that, I'm sorry. All right, that was an abstract class. What about for an interface? Okay, for that, I've worked hard to create this other example. I have a class devirtualization example and an interface devirtualization example. I'm just going to show you what the difference is between them. Yeah. The apply methods, I have changed them from func to ifunc. An interface that is the parent of the abstract class. That is the only difference in the programs. We're going to run that. There is a substantive difference here. We don't do CHA for interfaces. We only use type profiles. So we don't get that deopt the world pause. We do still specialize for the fact that we've only seen squares. So we get, when we introduce the second type, it gets made non-entrant. We specialize for 2 types, and so on. But we don't do that first step. Excuse me. That's the only difference. It's an important one. C1 actually will do CHA, and that's it. It doesn't use type profiles. C2 uses CHA and type profiles. But for the most part, you only need to worry about C2 anyway. That's our end goal. Oh, I should also point out to you what the implementation of also square, another square, and yet another square was. This is it. So which exec were we calling again? Oh, that one, in all 4 cases. But the type check was an equals. It's exactly equals this type, because that's an order 1 check. Instance of checks are order in. We're not messing with that. That's slow. So every type counts. This includes anonymous types, everything, so be careful. So HotSpot is actually really, really good at inlining. This is also true of your JavaScript engines, if you're wondering. It will inline anything less than 6 bytes. 6 bytes is enough for a setter. It is also enough for a getter. The maximum inline size is 35 bytes. It will do that if it's called at least 250 times. That's about enough for a moderately or not so interesting for loop. Fortunately, max inline size is not the maximum inline size. That's the frequent inline size. That's 325 bytes. That's quite a bit of code. And we'll do that if it's hot. What's hot? Well, called 10,000 times. Or cumulatively, invocations and packages. We'll do up to 9 levels deep of inlining. We'll do 1 level of recursion. The numbers change a little bit in tiered if you want to play with it. The easiest way to find these things out is actually to just run your VM with java-xx print flags final. It will dump a voluminous table of all the hotspot options that you could set. And it will dump the values that it has chosen for your piece of hardware. Note, these could be different from one system to another. So Most of them stay the same, but they do actually vary somewhat. Okay. All right, we're nearing the end. What I wanted to show you one more deop just for fun. I've got this. I've got a method. I'm calling it a factory method inside of a loop. I'm going to call it 100,000 times. Why not? Let's just completely overdo this. And I'm creating an instance of a class that doesn't exist. Why does it not exist? I forgot to put it on my class path. I don't know what I'm doing. I'm just going to catch that error. Why not? Let's just pretend like that didn't occur. What's going to happen? Well, you know the game. Right, this is my program. Obviously, this class did exist at the time I compiled it, but it's not on my class path. And yeah. It does turn out that we trap when you use a class that's not loaded, also a class that's not initialized. This kind of makes sense. The compiler would really be flying completely blind with an unloaded class. With an unloaded class, it doesn't know what fields the class has. It doesn't know the layout of the fields. It doesn't know what virtual methods the class has. It doesn't know the layout of the virtual table, the interface table. It doesn't even know the parent classes. It doesn't even know if it's a class or an interface. So, I think the last one's actually wrong. But anyway, it's really flying blind. It doesn't know. But hey, we'll compile the factory method, and we'll just put an unloaded trap in. And we'll go back to the interpreter in the hope that we can load it. Well, that didn't work out, did it? But hey, the method's still hot. Let's try to compile it again. And yeah, that didn't work out. And we'll try to compile again. No, that didn't work out either. And we'll just do this forever. Actually, not forever. There is a limit where it says, this just isn't working. I keep trying to compile and compile and compile, and nothing's going well. I give up. It just won't compile it anymore. But that's what's happening here. We're just continuing to compile it. And there's actually one interesting thing down here, too. At the very end, it says, made zombie. What's that about? Well, I told you, made not entrant isn't throwing the method away. It's not letting any new people in, because there may be someone already running it. And we can't just take it away from them. That's still a use. We can't garbage collect that yet, so to speak. But once it's finally done being used, we can go back and actually garbage collect it. So we move it to a zombie state, and then we actually reap it later. So made on entrant just makes sure that no new people start using it. Doesn't make sure that the ones that were already there are out yet. So you can see that was actually the very first compile 8, way up here, being made zombie. So, okay. Like, yeah, we could do the same thing for uninitialized, but I'm going to skip over that. You know what the game looks like. All right, reasons for deoptimizing. There are a few. This is the table. This is taken straight from the HotSpot source code. We covered a few of them. We covered class check. We covered bimorphic, unloaded. We kind of touched uninitialized, unreached, and constraint is actually CHA. So we covered a good maybe half. There are more. I covered the ones that actually happen most of the time. But why would you want to know this? I don't know. Unless you're just a VM geek. And you do need to know that these aren't all the same. I've shown you they do actually perform differently. If we did an implicit null check, we're probably popping the frame, throwing the null pointer exception. Maybe we don't actually have to go back to the interpreter. If we're doing it unreached, where we've eliminated a block, we're doing a trap. That's just a bail to the interpreter. It's not actually a deopt, stop the world pause. And even when we do something like that, we could decide, do we recompile right away? Yes or no? Maybe we actually keep the compile and do a recompile because this one's probably good enough, but we could do a little better. And there is the stop the world, oh my goodness, throw a bunch of things away case. And in that case, we actually throw them all away, and we go back and profile a while so we actually know what types are actually being used now. Because you've introduced a new type. Maybe you're going to use that everywhere. We're not sure. So we go back to the interpreter or C1 and gather some more data. We're not sure what to do just yet. These aren't always one-to-one, but this is pretty much what those actions in the previous thing, they were labeled on the bottom, correspond to in terms of reasons. The reasons you want to watch out for are the ones that throw your compilation away immediately. So those are things that, null check, yeah, that happens pretty frequently. Unloaded, yeah, that happens pretty frequently. Uninitialized, yeah, that happens. Yeah, you're getting the idea. The ones that hurt are unfortunately the ones that actually occur. Does this matter? Well, obviously, if you're doing performance benchmarking, it matters. Go use a tool like Caliper, or even better now, JMH, which is from the Oracle guys and is actually going to become the default tool, de facto standard tool for measuring VM performance, because you have to worry about warm-up. But the deop also creates volatility during warm-up, and it's not just for, say, one thread. The piece of code is shared between all threads. It's stored in a code cache, and it could be referenced from multiple stacks. If I don't let one person in, I'm not letting them all in. They're all going to have to go back to the interpreter. So it could be a slowdown across a whole bunch of threads, even though only one thread is experiencing the anomalous data. So it can hurt. And if it does hurt, well, that's exactly what I'm working on. So this is the one slide about Azul. This is what warm-up typically looks like in a VM. We get all this volatility from transitioning from interpreter to C1 to C2 and deopting a lot as we discover what the steady state of the application is. And it takes a while for it to settle down. It usually settles down quite nicely. What happens when you shut down your VM? We throw all that information away. It was just in memory. What ReadyNow actually is we store all this information off to the side. We know which methods are hot. We know what your application's going to do, as long as you don't change it too much. Yes, we will let you change it some. And we'll go ahead and compile all those things in advance with the same assumptions so that you're hot right away. And you won't even have those little deopt blips. These are those deopt blips. This is with my work. Fast from the beginning, minimal blips. So, all right. I hope you've learned something. If you'd like to learn more, this information's hard to come by. I'm not going to lie to you. But there are some places I can point you to. The Java Specialist newsletter by Heinz M. Kibbutz is pretty good for weird corner cases. It does go into deopt sometimes. IBM Developer Works articles are good for other types of optimizations I didn't actually talk about here. Lock optimizations. Those were written by Brian Getz before he worked for Oracle. He is now the Java language architect. He also wrote the concurrency book that hopefully you've read. Basically, just go read everything Brian has ever written. If you're interested about the internals of the VM, the OpenJDK wiki is meh. It's very hit or miss, but sometimes it's useful. If you really want information, I'd say you just have to go to the blogs of VM developers. Sadly, I don't blog. I have a toddler, and this is about all I have time for. But my colleague does. He blogs about performance issues. I was reading his blog before he was my colleague, so I recommend it. And despite working for Azul, I will tell you the Oracle guys do know lots and lots about how the VM works. Particularly Alexei Shipalev, who does their benchmarking. He's the creator of JMH, which I mentioned earlier. And then there's also, this is the Twitter feed of Igor Verasov, who did the tiered compilation work. I also sprinkled links across the bottom of many pages to more detailed articles if there was some particular thing you want to know more about. So, And if you'd like to play a bit yourself, there's a tool called JIT Watch, which will actually give you a UI to see a lot of this. It will show you the inlining tree visually. It will show you what got compiled. It will give you recommendations on how to improve your inlining. Can show you the bytecode. It can show you the assembler. It can show you all of this stuff. I just wanted you to see how it all works underneath. But it's sitting on top of all the same data feeds that I showed you. I haven't actually played with it myself, but it's been gaining a lot of popularity lately. All right. I hope you had fun. If you have any questions, I'll be happy to answer them.
May I ask you to return to the slides where you were explaining the traps, where you were basically introducing them?
Okay.
Yes. At this point, you were already talking about dynamic optimizations.
Yes.
But if we have a look at hot method, right, you see that both branches of the if statement are identical.
Yes.
Maybe I'm missing something. But
So it is entirely possible that you could do. He was asking, it does the same thing down both paths. So why did you need the test at all, right? Yes, that's a perfectly valid question. HotSpot applies optimizations first before it applies dynamic optimizations first before it does anything else. And so it misses out on seeing that those two things are the same. If it had looked a little harder, if it looked at those were the common first, then maybe it could have eliminated the test entirely and you wouldn't have the deopt. But it didn't do that. It could, you're right, theoretically it could. That's why I was poking fun of it.
is there any possibility to instruct HotSpot to do the opposite? Because
No.
if it could, then we could inline the system out print one.
And re-architecting that compiler to do that, oh, that's a 6-month task in itself, if not more.
So this is all about making your program go faster in terms of instructions. But I was wondering, so my program spends like 50% of the cycles waiting for memory. And I was wondering if HotSpot does any optimizations there in terms of memory layout and things like that.
I mean, there are all sorts of things that it's doing in terms of memory allocation and trying to be smart about where it's reclaiming memory and so forth. That would get into basically being a garbage collection talk, which I have one of. At this level, other than getting rid of heap allocation altogether, which just reduces pressure on the garbage collector, no, not exactly. So
It doesn't say, group frequently accessed fields together, things like that.
it does have some ability to do those sorts of things. I can't really say how often it does that. One of the things we're working on, we actually have a JET proposal to make it more memory subsystem friendly, more cache system friendly, by letting you lay out your structures in a way that's nicer for the cache. But that's a hard thing to express in Java today. So.
I was wondering, the volatile keyword there, do we need it? Is this a single threaded, right? So.
Not really. No, I could get away without it. It would probably still do it, but certainly with volatile in place, it can't make any assumptions because somebody else could change it. Well, modulo the fact that, of course, this is the only application class loaded, but details.
Hi. Actually, I was when you're explaining everything, I was thinking of the ReadyNow, the concept of ReadyNow, which is you are moving up all the work in the warm-up phase to something before, some static, probably during the actual compilation or something like that.
Yeah.
So instead of not just the warm-up phase, but what about all the interpretation being done in JVM? So what if I decide I want to run my Java program only in one processor, one architecture? Then I know, and also, and also, can we also move in that case, can we move all the interpretation phase plus the static optimization into the actual compilation and leave only the speculative optimization, which will depend on the profiling, not on the interpretation? Is it possible?
Certainly it's possible. Oracle is looking at doing ahead of time compilation for exactly the purposes of warm-up to not hit the interpreter. But yes, you give up the speculative optimizations to do it. The problem is that Java code is so heavily dependent on virtual calls and being able to devirtualize them that your performance just goes completely south. IBM can actually do what you're talking about today. They can do ahead of time compilation in a mixed mode way where you load your ahead of time compiled thing and you use it, but then you can also use speculative stuff on top of that. That has some nice properties, and it's not something we would rule out doing. It's just from our view that speculative optimizations are so important and so many Java programs are dependent on it, we didn't really want to give them up anywhere. So we just store the data and let the compiler do the same thing it did before. It does mean it increases our startup time because we have to recompile stuff. But we can also deal with small code changes too. If you had an inline method that changed a little bit, are you going to throw the whole compilation away? That's what you'd have to do with ahead of time compilation, or you'd have to do some late linking and then link time optimization. And most compilers aren't very good at that. So instead, we can say for the caller, use its profile data and maybe down a few levels. And then even if the callee, the one thing you're targeting, has changed, well, we can't use the profile for it, but we know it's hot and we can still inline it, right? So we can get a lot of benefit without having to throw the whole compile away, conceptually. So.
Just one small question, which is it at all possible to like speculative automation? Does it really need under compiler? Right? Does it really need the interpretation phase to be in JVM? Can't it be run on profiling data? If we add a lot of profiling in the binary, and also if we add all the debugging symbols,
certainly you could do that.
Which a lot of C and C++ tools do.
Yes, you could do that. You could do what a profile-guided compiler does, which is maybe you could use the machine's capabilities. You could instrument the code in some way and get your data that way. So you could say just do ahead-of-time compilation for C1 and start there and gather your data, and then use C2 for speculative. I mean, all these combinations are possible. It's just how much engineering effort and how much bang are you going to get for your engineering effort. So. Anyone else?
How often does this change? So what is the chance that the next minor release of Oracle VM is going to introduce a couple of new reasons for the optimization?
Yes, in HotSpot 9 that will happen. Right now, unreached means something particular. In Java 8, it is used only for pointer comparison sites. You notice I only use pointers types. I didn't use any integer types or anything else. That was deliberate. Those don't deoptimize. Right now. They used to in Java 5. They stopped doing that in Java 6. In Java 9, they're going to start doing that again. We just call it unstable if instead of unreached. So yes, it's a moving target. Anyone else? All right. Well, thank you all very much for coming. I hope you enjoyed it.